Hello everyone, hope you all are doing well. In this video, we'll discuss the last problem of Lead Code Weekly Contest 291. It's the hard level problem. The problem name is Total Appeal of a String. So in this problem, it says what is an appeal. So the appeal of a string is the number of distinct characters found in the string. Like for example, if we see this string A B B C A, so the appeal will be 3 because we have total 3 distinct characters in the string, that is A, B, and so this is the definition of an appeal. And given a string S, we need, we need to return the total appeal of all its substrings. So we need so for all the substring that can be formed out of this given S, we need to return the appeal, the sum of appeal of the substrings. And it tells what is a substring. So a substring is a contiguous sequence of characters within a string. So let's see example, one of the examples. So it's A, B, B, C, A. So what are the substrings that we can generate? So substrings of length 1 is the total number of substrings of length 1 are is A, B, B, C, A. That means all the 5 characters taken individually. They have an appeal of 1 each respectively. So the sum comes out to be 5. If we see the length, the substrings having length 2, so it's AB, BB, BC, CA, and so on. So the appeal comes out to be, for this one it's 2, for then this one it's 1, because we have only one distinct characters, and for the remaining 2 we have 2 each. So again the sum comes out to be 7. So we do it for all the substrings, and the sum comes out to be 28. Similar is the case for the second example. Now the constraints are that we have the length of the string is 10 raised to the power 5, and each character is a small case English character. So a brute force approach could be that we generate all the possible substrings and then calculate the appeal. However, that would result in big of n square time complexity, and that would be beyond the range. It would the loop would run in 10 raised to the power 10 time, and 10 raised to the power 10 times, and that is not the best of the approaches. So let's see how we can approach this problem. So suppose we have a string. Let's take again A, B, B, C, A. This was the string given. Now if we see what is an appeal, so actually we need to count the number of distinct characters in a particular substring. So another way to look into this problem could be that if we consider a character, if we consider this particular character, it's C right now. If we consider this particular character, so this this character can contribute at how many substrings? All the substrings that could be generated from here. Like for C, if we talk about, so it could be A, B, B. C could be one of the substrings with the last character at C. B, B, C could be one of the substrings from here to here. Another substring could be B, C from here to here, and the last one could be C. So we get total 4 substrings of of this string S with ending character as C. So that means for index number I, how many substrings can we have? It is I plus 1, because we use 0 based indexing, so it's 0 1 2 3. So for 3 we have 3 plus 1, that is 3 plus 1, that is 4 substrings. So yeah, this is one of the approaches. Now again, if you see what is an appeal is the number of distinct characters that we can have, that will have in a particular substring. So if this is the character that we are considering, suppose C, so C can only contribute in the substrings if that particular substring is not having C before beforehand. Like this can be only a contributor in a substring if that substring is not having C already. If this is a new addition, then only it will be a valuable thing. Like suppose if we have a substring C, then adding another C won't be increasing the appeal, because we already have two C's, and we need to count the number of distinct characters, and appeal is the number of distinct characters. So until and unless we add a distinct character, the appeal won't increase. So that means this C will be able to contribute only if the substring has doesn't have a C till now. So now what we can do, and suppose on the other hand, if 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 I talk about the character A, so we can see all the substrings ending at character A. So how many substrings will be there? There will be total one from this to this to this to this, one, two, three, four, five. Five substrings will be there. And in how many substrings can this A contribute? This A can contribute only in those substrings. Out of these five substrings, only those substrings which don't have an A. So this substring starting from here is has an A. So this A will not be able to contribute in this substring starting from A. However, this A will be able to contribute in all the substrings which start from this B, this C, and this A. So that means we need to keep track of the last position where we have seen the current character. So let's erase this and let's see what we mean by that. Just a second. Yeah, let's erase this. Yeah, clarity. So yeah, now let's see. So here we have again A, B, B, C, A. So for every particular index I, all we need to do is that we need to see whether in how many substrings has this character not appeared, ending at ith character. So all the substring ending at this character, uh, in how many of those substrings we don't have a C already. So that will be based on the last index of this C. So since we don't have a C till now, we can use a hash map for that. That what is the last index where we saw a C. We use a hash map or an array to keep the index. And if that is not present, that means this can contribute in all the four substrings, and we can just add the appeal that we have seen till now. However, if we consider this character, suppose B, now all the substrings ending at B will all the substrings ending at B, this B will only be able to contribute in the substrings which don't have a B. But we see the last index of the B is this only. That means index number 1, and this is index number 2. So this B will be able to contribute on only one substring, that is B. That is this particular substring. So this is the core logic that we consider only the substrings in which the last character will be able to contribute. Now let's come to the implementation part and get more clarity on how this can be solved. So yeah, again we take an answer variable and then we take an index. This index basically keeps track of the last index where we saw the current character. Since we have only 26 characters, English characters, so lowercase character, so we took a array of 26. We filled the array with -1 and then we started traversing the array. Now this is the appeal that we have seen till now. This is the appeal, because we saw now that the current character will have an appeal of the appeals that we have seen till now, plus the number of substrings that this character will be able to contribute. So we see that if the current character has not occurred till now, that means the position of the index is -1. So we just add I plus 1 to the previous string, because it's zero base indexing. So the number of substrings generated till index I will be I plus 1. So we add it. However, on the other case, if we have seen this character previously, then how many substrings will have a contribution? Like this character can contribute in how many substrings? So this will be I, that is the current position, minus the last position where this current character was seen. So this will be the appeal. We add the appeal to the answer, and we also update the index of the current character. And yeah, we do this for each and every character, and at last we return the answer. So hope you learned something new from this video. Again, sort of an implementation based question, where we just kept track of the last indices and just sort of use the techniques that we used in the third problem of sorry, the second problem of this contest. So sort of similar problems. So yeah, please do support this video by giving a thumbs up if you learned something new. Also do subscribe to the channel, and see you in the next video. Thank you.